Great. So I would like today to talk about what will be our final criterion for evaluating voting systems. This is what we've been on like sort of all last week. One more criterion. I hope you are maintaining a big chart as we've been revisiting every so often. And I think we have like 4 different columns in that chart, 4 or 5? I don't recall. But anyway, one last one, and it has a sort of a long name, which is abbreviated IIA. But you can add that into your big chart. I mean, I'll draw the chart in a little bit. But and I'll tell you what IIA stands for, but maybe first I'll just say what this is about. So similar, this on the surface will look kind of like the monotonicity, but it's not the same. So I will refresh your mind about monotonicity. This is what we talked about last time, and it said that if we change some ballots to boost the winner, then this doesn't change the winner. That's the monotonicity criterion. And the one that we're going to talk about today, the IIA, is similar to that, but not the same. And you'll have to try hard to keep it straight which is which. But anyway, if we change ballots to boost the winner, this doesn't change the winner. That's the monotonicity criterion. And the idea behind that is like, ideally, if you run the election, and then after the fact, somebody changes their mind, but they change their mind in a way which is supposed to help the winner out, then the old winner will still be the winner. More votes for the winner just makes them win even harder. That's the monotonicity. The IIA, so I will say IIA is also about changing votes, but it's changing votes in a different sense than this one. So this is also about changing votes, but not necessarily boosting the winner. It's actually kind of the opposite. It's about changing votes in a way which has nothing to do with the winner. That's the basic idea, and I will say more specifically about that. It's about changing votes without, I will say, any changes regarding the winner. So in the monotonicity, it's about raising the winner up in the rankings. The IIA is about moving around the losers, but not raising the winner up at all. It's sort of about shuffling the losers. Sorry, it's hard to read these words. I said this is about changing votes without any changes regarding the winner. I'm going to say more specifically, this is just sort of vaguely what this is all about. Here is, I thought we could demonstrate with a little example here. Let's say I have, this is a very simple little election here. 3 people said A, B, C, 2 people said B, C, A. And I'm going to use the borda here, just as an example. Remember, the borda is the one where you add up the points. I hope everybody remembers how to do the borda. The points, as you assign them, they always go 0 at the bottom. So here there's 0, 1, 2 are the borda points. And we add up using the borda. It's something like A gets, I hope you remember how to do this. You multiply the number up top of the column times the point position in each spot. So this A right here gets a 3 times 2. So this is 3 times 2. And then plus this A down here gets a 2 times 0. So that's 2 times 0, which is 6 plus 0, which is 6. Right? And then we could add up the other numbers. This B here gets a 3 times 1. I hope everybody remembers how to do this. This B here gets a 2 times 2. That would be 3 plus 4, which is 7. And then finally, C gets 0 in the first column, 3 times 0, and a 1 in the second column, 2 times 1, which is 1. All right, so using the Borda, the original winner is B. I said original because remember what we're going to talk about is sort of imagine what would happen if I changed some of the votes in a certain way. But B is the winner, and as I do when I'm talking about these sort of things involving changing votes, I find it helpful to just keep track of who the winner is by circling them. And then I'm going to talk about a specific type of change. Now, if I was talking about monotonicity, the change would be to boost the winner. That would be like to move this B up. But I want to talk about a kind of change which has nothing to do with the winner. And in this case, that would be like if these two guys, C and A here, let's just interchange their positioning, all right? So this is make a change which has nothing to do with the winner. Which, of course, in our example here is B, right? So in this example, actually, there's sort of only one change that you could make of this type, and it's right here. You might think, oh, can I just swap A and C? But actually, that swap would involve, say, moving C past the winner. So that would sort of, it wouldn't fall into this category of a change which has nothing to do with the winner. These guys right here, though, definitely does. So I'm going to swap the C and the A right there. And I'm not changing anything with regard to the winner, right? B is still above both of them. So I'm going to make this change. So BCA becomes B still on the top, AC. All right. And the important fact here is that here we didn't move anybody past the winner. That is, everybody who used to be under the winner is still under the winner. And everybody used to be over the winner, which was nobody in this case, still over the winner. All right? We didn't move anybody past the winner. And the idea of the IIA is that this kind of a change shouldn't change the outcome because I didn't do anything in terms of the winner, right? All I did was shuffle the losers around. Okay? Let's see, though, does this actually change the outcome or not? Actually, in the case of the Borda, you could think, I mean, I'm going to do the numbers in a moment, but on some kind of intuitive level, what's the effect of this change? The effect of this change is to give A little bit more points, right? And so actually it seems to me that maybe that would really change the results of the election. Anyway, let's just see what it goes. So the new version, after you make that change, it still says 3 people said ABC. Now these 2 people, they now say BAC. It used to say BCA, but I'm changing it to BAC. This is where the change went. Now we do the Borda again. So the points, of course, go 0, 1, 2 like that. And we add them up again. A now has 3 times 2 from the first column, and then 2 times 1 from the second column, which is 6 plus 2, which is 8, right? The B gets 3 times a 1 in the first column, and then a 2 times 2 in the second column. That's 3 plus 4, which is 7. And then the C gets 0 and 0, right? C is like the ultimate loser. I've been there, you know what I'm saying? All right. 0 points for C. And so A is now the winner. And this should be regarded as a weird fact about the Borda, that this can happen. So what happened here, I will just refresh our memory. We changed, so I will say, in the original votes, B won, right? Then we made a change which had nothing to do with B, right? All we did was shuffle around 2 of the losers. We changed up C and A, but that change had nothing to do with B. So then we made a change which had nothing to do, Get out of there. No. Struggling. All right. All right. We made a change which had nothing to do with B, but this resulted in A winning. And this is a somewhat unexpected thing. This change made A win. All right. Even though the change we made had nothing to do with B being the winner, actually it did change the fact that B was the winner. All right. And this example actually demonstrates that the Borda does not satisfy this IIA thing. So the IIA thing basically means if you make a change of this type where you don't change anything with regard to the winner, it should actually not change the winner. But in this case, we did make a change which had nothing to do with the winner, but it ended up by some weird fluke actually changing the winner. So let me just, I'm going to write this formally here. So this is called the IIA. Now the full version of this, you'll see why I don't want to say this every time. This is called the independence of irrelevant alternatives. Unfortunately, it doesn't have a cuter name than that, but I'm always going to call it the IIA. I think you can see sort of what sorry, I left a letter out of there. Irrelevant. I think you can see what the words here are getting at, though. The idea is if you make a change which has nothing to do with the winner, then that should not change the winner. Unlike the example we just saw, we made a change which had nothing to do with the winner, but it actually did change the winner. So the IIA, what it says is, if we do the election, and then make a change in votes. And what's important about this change in the context of the IIA is that you never move anybody past the winner. Like all you do is shuffle the losers around, but you never actually move somebody from below the winner up to above the winner. So if we do the election and then make a change in the votes, which never moves anyone past the winner. This is the important idea behind the IIA. Never moves anyone past the winner. It's so important, I'm going to highlight it. Never moves anyone past the winner, huh? Then, what should happen? Then, the winner shouldn't change. I mean, as a result of this change in the votes, then maybe I'll say this a little differently. Whatever. Then the results shouldn't change. This is the IIA criterion. If you make a change in the votes which never moves anyone past the winner, then the results of the election should not change. All right? Because such a change, if you're never moving anyone past the winner, the idea is that kind of a change ought to be irrelevant. That is what they call an irrelevant alternative. All you're doing is changing your mind with respect to the losers. It shouldn't make any difference. All right? This is the IIA. And the example up there that we just did, the example here actually was a demonstration that Borda does not satisfy this property, because in that example we made one of these so-called irrelevant changes, but actually it causes the winner of the election to be different. So the example demonstrates that Borda does not satisfy the IIA. All right. So in your chart, if you like, you can put a X in the Borda row for this IIA thing. Maybe I'll just because I actually want to talk about this a little bit more today, I'm going to try and write down the whole chart here. We have the voting systems where the plurality, the rank choice, I hope you have most of this written down already, the Condorcet and the Borda, and then the dictatorship, right? Dict And then we have, I'm going to try and write these in the same order, although I don't. We had the majority criterion first, and then the unanimity, and then the Condorcet winner criterion. How am I doing so far? Am I writing them in the same order? Yes. Then the monotonicity, right? Oh, do you have a question?
So in the example we just did, where like you switch it and then A and then more comes down.
Yes.
That won't usually happen if you switch it.
Yeah. The idea is if all you do is change around the losers, then on some kind of intuitive level, if all you're doing is changing your opinion about the losers, that shouldn't matter to who wins. But it turns out in the Borda, actually changing your mind about the losers can change who the winner is. Yeah, so this you should regard as kind of a weird thing that happened in this particular example. But it can happen. Yeah. All right. Sorry I didn't see your question before. The monotonicity, and now we are talking about IIA. And I think this is, I have the whole chart, right? I'm just trying to remember this. And now, what about all the things in here? People have been asking me, getting ready for the test, are we supposed to have this whole chart memorized? And my answer to you is no. But you should be able to think through any one of these. So like I might ask you on the test, explain why plurality satisfies the majority. So I wouldn't necessarily expect you to have that fact memorized, but you should be able to explain it. And the explanation in this case involves writing a little proof about the majority property. So anyway, this does satisfy, the rank choice does satisfy, the Borda does not, and the dictatorship does not. I believe that's what I said last time I wrote this chart. Anybody agree? Okay, and the unanimity, like I also don't have all of these things memorized, so as I'm trying to do this right now, I'm trying to reconstruct in my mind. Everything satisfies the unanimity. The unanimity, remember, just means if every single voter thinks that X is better than Y shouldn't win, which is very, very easy to be satisfied. The Condorcet winner, most of them do not satisfy, although the Condorcet method does. These other ones don't, though. The monotonicity, this is the one we just talked about last time. Plurality does satisfy, but rank choice does not satisfy. The Condorcet does, the Borda does, the dictatorship does. Right? And now, today, finally, we're talking about IIA. And the IIA, what we just have already talked about is Borda does not satisfy. Right? Borda is looking kind of bad in this, as far as this chart in particular goes. Although this chart is just you could say, just sort of a random jumble of a few different ways we could try to evaluate these things. Although it's not to say that Borda is necessarily bad. I mean, in this case, we have like 3 checks for plurality, but only 2 for the rank choice. That doesn't necessarily mean that plurality is better. It just means, according to these 5 specific measures, plurality is doing a little bit better. Anyway, let's talk about the others for IIA. So on your homework, as usual, I like to leave some of these for you to try on your homework. So on the homework, this IIA thing is actually a hard property to satisfy. So on the homework, you'll see that plurality and RCV, the rank choice, both of them do not satisfy IIA. So I'm going to put X's on those. What about the Condorcet and the dictatorship? Actually, I'm going to put the dictatorship on the homework also. And that one does satisfy, so there's going to be a check for the dictatorship. Dict does satisfy IIA. All right. And what about the Condorcet? I thought we can talk about the Condorcet method right now. So the Condorcet does satisfy. Now, as usual, if you want to show that something does satisfy one of these properties, you have to write a little proof. And as usual, the little proof that you write, the structure is always basically the same. You just have to kind of fill in the middle part. So let's show that what am I talking about? Condorcet. The Condorcet method satisfies IIA. All right, we have to do a little proof here. And what does it look like for the IIA? Remember, the IIA is about if I have a particular winner to begin with, and then I change the votes in a certain way, and then you have to explain why the winner doesn't change. So I'm going to begin, all of our little proofs always begin with some kind of imagining scenario. You imagine, so in the case of the IIA, we say something like, imagine that X wins using the Condorcet method. And then we change ballots without moving anyone past X, right? That's what the IIA is all about. It's this kind of change. You change the ballots, but you don't move anybody past the winner when you are shuffling around. A more informal way of saying this is all you're doing is shuffling around the losers. You don't actually take a loser and push them above the winner, or take someone above the winner and push them below. All right, so we imagine that X wins using the Condorcet method, then we change the ballots, blah, 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 and we conclude, thus, X still wins using the Condorcet. Of course, the Condorcet is what we're talking about in this particular case. What you have to do is fill in the blanks in the middle with, and as usual, if you know what you're doing, you can write the middle part in usually just a sentence or so. In this case, we have to think about in terms of the Condorcet method. Anybody remember what's the Condorcet method all about? Yeah?
Like whoever wins all their 1v1.
Yeah, that's about all the 1v1s, she said. You group them in individual pairs and you see who wins all of them. So in this case, we are imagining that X wins every individual pairwise matchup. And then you do one of these changes. Your change is without moving anyone past X. Does that mean that X is still going to win all those one-on-one matchups? Like, for instance, if I have, there's just some other candidate, X against Y. Now, in the original election, X beats Y on a one-on-one. Do you know that X is still going to beat Y after you made this change? Can anyone explain why? Yeah?
Wouldn't X still win because it would still have one to votes, even if you boosted Y?
Yeah, how do you know, how do you know that Y doesn't get more than X after you change it?
Not supposed to.
Because it's not supposed to. Yeah, I mean, it's because I said the change is without moving anyone past X, right? I think this is what you had in mind. Since we don't move anyone past X in these changes, it means the change cannot affect any of these one-on-one comparisons, right? If X was going to beat, Biden before, X is still going to beat Biden because none of these things are moving Biden past X. I don't know why I started saying Biden. He's not even running. Okay, so what you say in the middle has to be some version of what I just said. Of course, there are many ways to say this. Maybe I'll say X will still win all their 1v1 matchups, since no single opponent got moved past X, right? That's the whole idea of the IIA kind of type of changes. Because we changed the ballots without moving anyone past X. That means if X was going to win all those one-on-ones, they're still going to win all those one-on-ones. All you did was shuffle the losers around, so maybe the loser one-on-ones, maybe some of them got changed, but not the ones involving X. That's the idea. Thus, X still wins using the Condorcet method. All right? So the Condorcet does satisfy the IIA. All right. Any thoughts or questions about that? This is the IIA criterion. In my opinion, this might be the weirdest one. I don't know. It's something that's can be a little confusing about it is very similar to the monotonicity criterion in that they're both about making some kind of a change after the fact, but they're different types of changes, right? Monotonicity is you change by boosting the winner. The IIA you change by moving people around but never moving them past the winner. So it's different. All right, great. Let's, can we just look at the chart here a little bit? I want to talk, maybe I'll just copy this down, although it doesn't really matter, I suppose. We're not going to make this chart any bigger, so this is the end of it. Oh, we should put a check under the Condorcet. That's what we just discussed, right? There's a check right there. Condorcet is actually the only one of any of these that satisfies, well, no, and the dictatorship, all right? But those are the only ones which satisfy the IIA, all right? It is natural to step back a little bit and look at this chart now that we know a lot about these. Which is the best system? Which is the best? Well, looking at the chart here, I mean, like good is a lot of checks, right? The checks are good because they mean that the system is fair in this or that way. The X's are bad. There is, of course, the Condorcet has checks everywhere, so it would be tempted to say that the Condorcet method is the best to be used in real life. There's actually a good reason that that's not actually the case. Anyone recall? There's a reason why the Condorcet method is not actually suitable for real life, say, political elections. It's not. The Condorcet method is the one where you do all the one-on-one comparisons. You certainly could try this in real life. There's a sort of big reason why we don't do this in real life. Yeah?
Sometimes it's just wrong, right?
Sometimes.
Out with the wrong winner.
I wouldn't say that. I would say that kind of does happen with plurality and the ranked choice. Like, for instance, in the Bush-Gore-Nader thing, Bush was the winner in real life, even though kind of, in my opinion, Gore should have been the winner. Or the Begich thing was messed up also. I liked your answer. You said, because sometimes. I thought you were going to finish. Anyone have another sentence beginning sometimes? There are reasons why we don't do this in real life. You've seen it on the homeworks. Yeah?
Sometimes no one will go.
Yeah, sometimes there just straight up is no winner with the Condorcet method, all right? And, of course, it's possible to get ties in any of these methods, but in a large election, a tie is basically, statistically speaking, never going to happen to get an exact tie. But with the Condorcet method, it's not actually all that unlikely. So for this one often gives no winner. And so that's sort of a major issue. You wouldn't want to use this one in politics, and as far as I know, this is not used anywhere in real life politics for this reason. Because if you do the whole election and then you just say, well, I guess nobody won, then that's an unacceptable result for a real life political election, all right? So, which is best? According to the chart here, the Condorcet looks like the best, but actually you can't use the Condorcet in real life. The one thing that I would like to keep in mind is that this chart is only expressing, these 5 particular ways that you could judge how fair the systems are. These 5 criteria. And there are other ways that you could there are other ways to evaluate them, right? Which, actually we could spend the entire semester doing more and more and more of this, although I want to mix it up a little. I don't know. I hope that this seems interesting to you all, but I don't want to talk about this exclusively the whole time, but there are many, many other ways that you could try to evaluate systems like this. And actually, there are many other voting systems that you could try to talk about. If you looked at the homework, you'll see I had you learn about another type of voting system. There are other ways to evaluate them. So you shouldn't just look at this chart and choose like your favorite one to use in real life based on the checks and the X's. I've told you several times before that, in my opinion, actually, I kind of like the ranked choice in real life. I don't really like the plurality in real life, although according to this chart, the plurality has more checks on it than the ranked choice. But that doesn't necessarily mean that it's better. In fact, the dictatorship has more checks than the ranked choice, which certainly I don't believe that the dictatorship is better than the ranked choice for use in real life elections. Which is the best? The question, I would say, I would just put another question mark here. Like, this is not something that you can answer with any sort of mathematical certainty. Really, when it comes to using these systems in real life, you have to think about what is important to me about how the system works and choose a system appropriately. All right. What I want to talk about for our remaining 15 minutes or so is, like I said, there are other voting systems too that you could try to come up with. One big question that you could ask is, like, okay, these 5 that I wrote here, there's kind of pros and cons of each one. But I don't know if you've ever thought about, could we design some kind of other system, another way of counting up the votes, which satisfies all of these? I mean, the Condorcet method does satisfy all of them on the chart, but the Condorcet method is not suitable for use in the real world because it doesn't always choose a winner. So the natural question is, can we just try to think of a maybe some kind of more complicated system which actually always gives you a winner and also satisfies all of these things? And unfortunately, there's sort of a bad news answer. Could we design another system which satisfies all of them? The answer is no. This is bad news for lovers of democracy. It means that actually no system can satisfy all of these properties and always choose a winner. So the Condorcet method technically does satisfy them all, but it doesn't always choose a winner. That's the big problem. This is the bad news. And when I say no here, there's kind of 2 ways that you could interpret this. So, can we design another system which satisfies all of them? The answer is no. There is no system which satisfies all of them. But what I mean is, actually, there cannot be such a system. So what I don't mean it's not discovered yet. I mean it's logically impossible. Sometimes, if I'm talking about voting systems to ordinary people, like in the club or whatever, when I meet people, and I'm naturally talking about different voting systems in the club, and they say, and I say, like, the interesting thing, to me, like, this is the heart of what's really interesting about this. The interesting thing is that there can be no perfect system. Like, we have many ways of judging whether a system is good or not, and actually there is no system which is good in all of the ways that we want it to be. And often the response in the club is, oh, well, I guess we got to just work harder and figure it out. Like, work harder to design a system which actually does satisfy all these things. And my response is, no, you don't get it, man. It's not that nobody knows about it yet, or we just haven't discovered it yet. It's that actually it's straight up impossible. So this was actually proved. When I say something is logically impossible, I don't mean a lot of people tried and just nobody figured it out. I mean actually somebody proved, and we're not going to try to do this proof in class, but somebody proved it's impossible. And this was done in the 50s, the 1950s, and I'm going to write specifically what exactly has been proved. This is called Arrow's impossibility theorem. And this is like one of the impossibility theorem. And this is from the 1950s. And this, I would say, is the biggest kind of mathematical theorem in the area of different voting systems. This was, in some ways, the original big theorem about this, which actually convinced people that these systems were mathematically interesting and not just some kind of curiosity. This is called, and it's this name Arrow. This is like a person's name. This is this guy Kenneth Arrow, who was actually not a mathematician. He's an economist, but he studied this is one of those things that economists study sometimes, like group decision making. And of course, voting is a standard way of making decisions in groups. And so this guy Arrow won a Nobel Prize in economics for other stuff, not for his work in the mathematics of voting. But anyway, the impossibility theorem, it says, this is what Arrow proved: the only system satisfying the Condorcet-Winner criterion and the IIA is, actually there's one on the, I should say, sorry, the only system which always chooses a winner. I forgot to say that because the Condorcet method doesn't count. The only system which, sorry to squeeze this in, always chooses a winner. I gotta move all of this. Sorry about that. It's easy for me. I know it's a lot harder for you. The only system which always chooses a winner and satisfies the Condorcet-Winner criterion and the IIA is, anyone know what I'm going to say? You can tell if you look at the chart. There is only one system which satisfies both of those. Anyone say it? Shout it out. The Condorcet method doesn't count. Can anybody see the chart? There's only one system which satisfies.
The dictatorship?
It is the dictatorship. Oh, I put the X here. I think that's wrong. I think I had misremembered that. Oh, no, I'm sorry. What's wrong is right here. It should, that's why everybody's puzzled. This is a typo. It's unanimity, not the Condorcet winner. Sorry about that. The only system which always chooses a winner and satisfies unanimity and the IIA is dictatorship. All right, I got it right now. All right. Another way to say this, or this is kind of like the hot take version of this, if you want to tell your friends at lunch, the hot take is the only perfect system is dictatorship. You can shock your friends and grandmas by saying this is what you learned in your math class. All right? There is a mathematical sense in which this is correct. The dictatorship actually does perfectly accomplish the goals that the dictatorship system is meant to accomplish, which is to say that one guy gets to make all the decisions, right? Like that as far as what the system is meant to be, it is exactly what it is meant to be. All other systems, though, all other voting systems have some kind of weirdness to them, where they in particular, they cannot both satisfy unanimity and the IIA. Any chart, this means like any kind of version of this chart that you want to make, any system will always have some X's in it. Other than this one, which doesn't give a winner, which you can't use in real life. All right, this is Arrow's impossibility theorem. This is a big sort of, it was, like I said, kind of surprising at the time when it was discovered, and it was immediately recognized as significant. As far as what does this mean in real life, to me what it means in real life is that, like I've said, there are lots of people in our real life politics who think we should change from the plurality to the ranked choice. To me, like from a sophisticated mathematical point of view, I can say like, yeah, I kind of like the ranked choice a little bit better, but like from an abstract mathematical point of view, I would never say the ranked choice is the best system. I would say there is no such thing as a best system. You just have to decide what you want and choose a system which most of the time does what you want, but you're never going to be completely satisfied. You should never be completely satisfied. That's why I'm skeptical of people who are real diehard ranked choice lovers, as if it's somehow some kind of a perfect system. It's definitely not a perfect system. All right, that is Arrow's impossibility theorem. And I think that's all I wanted to say for today. Would you mind leaving a few minutes early? I hope you won't mind.